this is some work I did in my internship in Oxford 1 year ago. So with Nathanaël and some other guys, Joël Ouaknine, Amaury, Pouly, and James Worrell. So I'm a student at ENS de Lyon, and right now I'm an intern with Nathanaël here in the Turing Institute and in UCL also. Okay, so we're going to talk about linear dynamical systems, and the question is to study the point of view of invariants. So we're gonna see all of this. So the first question is the so-called orbit problem. People also call it the Cannon-Lipton orbit problem because they solved it. They were the first one to give decidability in the 80s. So the question is like this. We have a matrix and we have two vectors. And we ask whether when you apply your matrix to vector x, do you reach y at some point? So this is equivalent to saying is y in the orbit of x, which is the set that I will write O in this talk, this presentation, which is the set that you obtain when you apply matrix A to vector x. So for example, we can have this instance in 2D. You have vector x, vector y, and then you can draw the images, and you see that the orbit will just go to infinity. And in this instance, the answer is no, we don't reach y. So it seems pretty easy to see right here that the orbit is going to grow big, and yeah, so that's the intuition. In this example, we're given a rotation, also in R2. So we have a rotation of angle theta, and we ask, going from this point, can we reach this one when we apply our rotation? So the first case is if theta is a rational multiple of 2 pi, then we have a finite orbit because it loops back on x. So we just have to test whether y is or not one of these finite sets of points. Now the other case, which we all know, is when theta is not a rational multiple of 2 pi. So here for the drawing, I have a slightly smaller theta so that I don't loop back on x. And you all know that this is going to give, as an orbit, an orbit that's dense in this circle. So actually here the answer is no. This orbit doesn't touch y, but it gets arbitrarily close. So this is the point where we start to see that maybe this problem is not so easy. There's not only cases where, it can happen that y is really, really close to the orbit, but actually not in the orbit. So that's kind of the complicated case of the problem. Okay, but my point is not this. My point is, what about invariants? So what's an invariant? An invariant is just a set, so that when you apply your function to any points of the set, you remain in the set. So what could be a way, in this case, of showing that y is not in the orbit? Well, the intuitive way to do this is to say that, okay, at some point we get big, and then we remain big in norm or in a way. So a way to formalize that is to give a set, an invariant, okay, so here I give the set of UVs such that both are positive and the sum is larger than 7. With this matrix, it's really easy to see that this is an invariant. Because if both coordinates are positive and you apply this matrix, they remain positive and they grow, so the sum will grow, right? And then if I just add points x and ax, I get these three conditions. So my set is an invariant, I contain the start vector x, and I avoid y, okay? So this is what I'm gonna ask of my invariant, and when I can have a set with these three conditions, then I know for sure that y is not in the orbit, okay? So here we can note that we had the intuition of a general thing that can happen is that, okay, so assume that we're given x, okay, and now we want to ask if there's an invariant. So if we know that y is out of the orbit, in this case, the 7 here, we can always change it to some arbitrarily large number, so we can push our invariant further back, and then we will always be able to have it big enough so that y is not in the set, okay? So in this instance, whatever point y out of the orbit, we are always going to be able to synthesize an invariant, okay? So this is an intuition that will be helpful in the proof. If I'm not clear, please do interrupt me, because we have some time, so yeah. Okay. So what can we say in the case of the rotation? Well, in the first case, it's easy to synthesize an invariant. We would just take some safe zones around each point and make it so that it's invariant. Okay. For instance, some balls like this is going to be a good invariant. What about this instance? Well, if we ask that our invariant is closed, which is some really natural thing, like, I mean, topologically closed, people in dynamical systems, I think they always prefer to work with closed invariants. Well, if my invariant is closed, then since it has to contain the orbit, it's going to have to contain the circle, and so it's going to have to contain y. So in this instance, I'm not happy. There's not going to be a good invariant that's satisfying for me. So the invariant that I could still take is the orbit itself, but this obviously is the thing I want to avoid doing, because the goal of this is to have actually an invariant that's of some form that I can manipulate, and yeah, the orbit is obviously not the solution I want to have. Okay, so let's try to formalize this. Oh, no, sorry. First, we're gonna see like some examples of why having invariants can be helpful in real life, like applications of this. So let's say we want to have a program that computes the square root of an integer n. Okay, so a program that does this is this. Okay, I'm saying to you that this computes the square root of n, but why? Well, invariance can be a way of proving that a program computes something. Okay, so what can I do here? I can say that my start vector is x is 0, 0. Okay, it's the start of my program. And then my function is what's happening in the loop. Okay, so it's exactly to a vector uv. I multiply by this matrix that you see here. And then I add this +1, -1. Okay, so this is the dynamical system that actually is underneath this program. Okay. And then let's say I set this bad location that I want to avoid. So now it's a set, it's not just a vector. Okay, by the way, here we have an affine transformation, but we can always add a dimension and then treat this like it was linear. Okay, then if we can synthesize an invariant, say this one, so I have 3 conditions. The first coordinate squared is the second one, and then I have some inequalities here. And my claim is that this invariant proves that the program actually computes square root of n. Why? Because, so this is invariant, you can check it, it's not too hard. And then it's, yeah, the fact that this is invariant tells me that at the end of my program, sorry, I haven't done this slide in a while. Yeah, if my program stops, I know that j is bigger than n, because I'm out of the while loop. I know that j is I squared, because that's the first condition in my invariant. And I know that it's smaller than n plus 1, because it's the second condition of my invariant, okay? So this exactly tells me that I is the square root of n, okay? Okay, that's like just to motivate the use of invariance in general. Okay, another topic in which we use invariance is static analysis. When you have a program with a while condition like this, it's really like invariants are appropriate to study this. So if I'm given x and then I have a linear while loop, if I can synthesize an invariant for the matrix that I apply in my while loop, and that contains my initial location, then I know that at the end of the while loop, I'll be in the invariant. But then if I add another while loop with a matrix B, and say I can synthesize an invariant, a green invariant that contains this one, then I know that whatever happens, if I can perform these two while loops and an AND, I'll be somewhere in the green location. So here we see that it's like somewhat dynamical. If you can have an invariant for a program, then it can be the input for another invariant synthesizer. Okay, so that's kind of the framework we would like to work in, and we would like to have some results. Can we find invariants? And okay. Yeah, so we have some modularity. Okay, now let's forget about this and let's have a concrete definition of our problem. Okay. So we're given a start location, a starting vector, and a bad location that we want to avoid. So this is back to the formalism that we had at the beginning, and a linear transformation. And then what I call an invariant domain. So this is like the type of invariant that you would like to synthesize. For instance, this could be like circles or polyhedrons. So this is a set of sets. Yeah, so that's like a type of invariant, okay? And we ask, does there exist a set that has this form, so in D, that is invariant, contains the source location, and avoids the bad location? Okay, so this is what I'll call a good invariant. These three conditions. So by the way, yeah, so the main motivation of this could be to give a certificate for a no instance of the orbit problem. Okay, so I think that's probably the best way of seeing this. Okay. Okay, so we want to show some stuff about this, but probably we're gonna have to be more specific. Like if we're gonna have to fix an invariant domain, and then we can give some results. Okay, so what invariant domain could we think of? I'm just gonna define some sets, so some types of sets. So what's a semialgebraic and semilinear sets? So this is what my results are gonna be about. Okay, so first, a semilinear set is a finite union of polyhedra. So yeah, so this is a semilinear. It's any like sharp shaped set is a semilinear set, okay? And then a semialgebraic set, so that's given by a Boolean combination of polynomial inequalities, so on the coordinates. So for instance, a circle is given by this equation, so sorry, a disk. So a disk is a semi-algebraic set. Or a circle is a semi-algebraic set because the equality can be smaller and larger. Or you can do a lot of sets are semi-algebraic. That's a really rich class of sets. Okay. Okay, so what invariant, just to motivate, why did I choose semilinear and semi-algebraic in my setting? Well, sorry. So the challenge is that there's always a trade-off. If you have a really simple class, then it's going to be really easy to manipulate. But if it's too simple, then invariants are not going to exist in general. Okay, so there's this trade-off that we want a class that's rich enough so that invariants exist in cases of non-reachability, so when y is out of the orbit. But at the same time, we want an invariant that's easy to manipulate for our applications. And also, what we could want is that the set of invariants is such that it's easy to check invariants. Like, that's a reasonable thing to ask. Okay, so the first idea would be to consider polyhedral invariants, because that's also what's done a lot in practice in static analysis. The inconvenience with this is that polyhedral sets are always convex. And when we are having a linear transformation, well, in most cases, you're going to have an eigenvalue that's complex in the sense that it's not real. So it means that something is going to turn around in my orbit. And when something is turning around and that you have a convex set, well, the set has to be really big, right? So for instance, in this example, where we have a really simple rotation that gives a finite orbit, well, there's going to be no polyhedral invariant because y is in the closure, convex orbit of, in the convex hull of the orbit, sorry. Yeah, so here we can't have any polyhedral invariant. So one way to relax this is to allow for finite unions of polyhedron. That's why we introduce semilinear sets. So here we have a semilinear invariant for this transformation. Okay, but actually semilinear still aren't that rich. There's actually a lot of cases where there's going to be no semilinear invariance. Okay, for instance, in this case, okay, so y has positive distance from the orbit. We're in the case where we have an orbit that's dense in the circle. And my claim is that there's no semilinear invariant in this case. So why is that? A first try would be to so we have to contain the circle. So let's have this, this is a semilinear because it's the union of these four rectangles, okay, and it contains the circle. Then the problem is that this is not invariant for this transformation. Why? Because it would have to contain the image of this point, which is somewhere here. And also it would have to contain the image of this point, which is somewhere here. It doesn't, okay? And the intuition is that if you want to contain the circle in some semilinear set, then you're going to have some edges, and then there's going to be a problem with the edges, okay? Okay, so this is not invariant, and so we're not that happy with semilinear sets, okay? The natural choice here would be just to take as invariant the circle. And that's where we see that maybe semialgebraic is actually a good class, okay? So my main result is going to be with semialgebraic sets. Yeah?
So this might be silly, but if you could just go back to the last
yeah.
one. So, I mean, what you want to show is that your orbit avoids y, right?
Yeah.
So, I mean, it's not necessary for the invariant to be closed under your transformation. It's just that it needs to contain the orbit and not contain your y, your bad point.
Yeah, but yeah.
I can definitely see why you want the circle there, because it's much nicer.
Yeah. Well, the whole idea is to actually have an invariant. So
checking that the orbit is included in there is equivalent to the problem.
yeah.
You don't have access to the orbit. Right. Okay, I see. Yeah.
Okay. Okay, so semi-algebraic sets seem good. And in what cases are there no semi-algebraic invariants? Well, in this case, we already saw where y is actually in the closure, the topological closure of the orbit. Well, we're not going to have any closed semi-algebraic invariant. So the domain we would want would be anything, so that we can take the orbit itself. But this is a bit silly. Okay. Okay, let's move on to the main results, which we published in STACS this year. So first, an observation is that if y is in the closure of the orbit, then there cannot be any closed semi-algebraic invariant, right? This is okay. But then the result is actually the converse to this. So it's positive results that says that whenever y is not in the closure of the orbit, well, actually there exists a semi-algebraic invariant, okay? So yeah, I like to see it as a math result that just says, okay, there exists a semi-algebraic invariant, but actually our proof is constructive, and it gives some results about decidability and the size of an invariant, of a representation. yeah, so in particular, this is decidable in p space, whether y is in the closure of the orbit. So we'll see why in the proof. Like these are both corollaries of the proof, actually. Yeah, and this, yeah, it's just that in the proof, whenever we synthesize invariants, they always have a polynomial size representation. Okay. Okay. How much time? Yeah. Okay. Let's move on to the proof. I think we can we have some time to see the tools I used. And, okay. So the general idea is that when we want to work with a linear transformation, we're gonna just work on what's called Jordan blocks. Okay. So we put the matrix in Jordan form. So that means it's diagonal with blocks, and the blocks are Jordan blocks. So that this means that we have an eigenvalue on the diagonal, and then eventually some ones up there. Okay. So if the matrix were diagonalizable, that means we would have only trivial Jordan blocks. So Jordan blocks of size 1. When we have a Jordan block of size 1, then there's no ones that appear. And then when the matrix is non-diagonalizable, then that means that we have bigger Jordan blocks. Okay, so this is like classic results. So now we're working in the complex numbers, okay, because we need an algebraically closed field in order to put our matrix in Jordan form. Okay, and then the general strategy is going to be this. So we change bases to have this cool form. And then we look at our blocks. If one of the blocks is convenient, I'll explain what this means, then I can construct an invariant just for this block, okay? But when I have an invariant for one block, then it's easy to expand the invariant for the whole matrix by just saying, yeah, so let me write this on the board maybe. Okay. So let's say, so my matrix is a block matrix. And let's say I have an invariant for one block. So let's say I have, so this is a block of dimension, let's say D, and this whole is of dimension S. Let's say I have a P in C to the D. That's invariant for this block. So so this is such that the projection on this block of X is in P, and the projection of Y is not in P, okay? Then my claim is that I can have an invariant for the whole matrix, and this is just by taking Q is the set of Z's in C to the S, such that the projection of Z is in P, okay? So this is clearly, this is invariant because, oh yeah, I didn't say, here we have block B, here we have matrix A. P is invariant for the block, so that means that BP is included in P, okay? So why is this invariant? Well, if I have a Z, the thing is that the fact that this is diagonal means that the coordinates that are not in this block will not interfere when we check invariance. Yeah, so it's fairly easy to see that Q is invariant, and then it contains X and not Y. Okay, so this is not the hardest thing. Okay, so that's how we extend invariant to the full matrix, and then we can do the base change. This doesn't change the fact that the invariant is going to be semilinear or semialgebraic. Okay. Okay, so what's a convenient block? So we have our blocks, and then what I say is that we have basically 4 cases, okay? In the 3 first cases is cases where I can find a convenient block, and the 4th cases is the case where there is no convenient block, okay? So if I have an eigenvalue that's of modulus bigger than 1, then I can just go in this block and make an invariant for this block. Same thing if I have an eigenvalue of modulus smaller than 1, or if all eigenvalues are of modulus 1 and the matrix is non-diagonalizable, then it means that I have a non-trivial block, so of size bigger than 2, and I can work in this block, okay? So then the last cases will be this one. So this is the more subtle case where some real number theory happens. So this is what we're going to see at the end. But first, I'm going to detail the 3 first cases where I have a convenient block, okay? So now I just have to work in one block and to see if I can find an invariant for a given convenient block, okay? So let's do the first case first. First, we can also reduce to this. We can assume that x and y are both non-zero on each block, so the projections. Why is this? It's, well, if, for instance, x is 0, then an invariant would be just singleton 0. So, and if x and y are both 0, then you can reduce to the problem where you eliminate this block. Well, this is not, okay. Okay, so first case is if I have a convenient block that is like this. So if I have an eigenvalue that's of modulus bigger than 1, okay? So my setting is that my matrix is like this, and x is a non-zero vector. So I have coordinates, and then I take xl to be the last non-zero coordinate. Okay, so maybe it's the last, but okay. Why do I do this? Well, if I work in coordinate L, then if I look at ANX coordinate L, it's just going to be this, okay? Because the 1 will be facing a 0. I don't know if I'm clear, but I have a good, what I call a diagonal behavior on this coordinate, meaning that when I apply the matrix, I just multiply by lambda n, okay? So what happens? Well, we have a little picture here. So this is the orbit. This is the L coordinate of the points of the orbit. And then it grows and goes around. So at some point, it gets bigger in norm than YL. Yeah, so when I look at the 4th point in the orbit, it's already bigger in norm than Y. So I can just take P to be all points that are bigger than this one. So this avoids Y. This is invariant because whenever I have a point here, well, the image will be bigger in norm. And so this is a good invariant. So I just say that, yeah, now I add some singletons, as I did in the beginning. And then I can say that, so P is going to be the set. So for this, I'm just going to write this down because this is so that we all have it. And I'm not going to do this for the cases afterwards. But here I have P is the set of, so did I specify? No. Okay, let's say C to the D, such that ZL is bigger in norm that yeah, and then, sorry. So this as such is not invariant, but if I say I add that I also have to specify that the coordinates afterwards are non-zero, otherwise it can come and interfere. So I have so this is my invariant, and then I can deduce an invariant for the whole matrix. Okay. Now, second case is if I have an eigenvalue that's of modulus smaller than 1. So here it's we could think that it's exactly the same. It's going to go to 0, and I have an invariant that's like quite the same. Actually, it doesn't work so easily because if I look at the last non-zero coordinate like before, we're going to have a diagonal behavior and it's going to go to 0. But then maybe on this precise coordinate, y is 0, okay? So I cannot exclude it by saying that I'm going to be smaller in modulus. Okay, so in this setting, I have to reason on the whole vector. So what's still true is that a to the n x as a vector is going to go to 0, okay? So I said that y, sorry, there shouldn't be an L here, it's a typo, it's just y. So y is a non-zero vector, so at some point I'm going to be smaller than y in norm. And then I want to say I'm going to take as an invariant a small ball so that I'm smaller than y, okay? The problem is that the ball is not invariant, okay? Because let's say I'm just in 2 coordinates. Yeah, so I'm in 2 complex coordinates, okay? And if I take a point here and a point here, okay? So my point is this and this. Then I apply my matrix. I get lambda times this plus this for the first coordinates, okay? Because my matrix is like this, okay? So I go like lambda, and then I add, okay, that's not the good example. Let's say that lambda takes me here, and then I add this, well, I get here, okay? So I get out of the ball. So the ball is not invariant, but what I can do is I'm just gonna, so to fix this, I'm just gonna define another ball that's a bit different, that says that if the coordinate is big, then like the bigger the coordinate, the smaller it has, the number has to be in norm. Okay, so this is actually invariant. So there's a little drawing here to explain why it's invariant. So let's say I have a point in there. I'm looking at coordinate L, okay? So ZL is here in this ball of this radius, okay? And then when I apply the matrix, so AZ coordinate L is this number, okay? So what do I do is I rotate and I shrink a little bit, okay? So I get here. And then I add ZL plus 1. But ZL plus 1 is in a smaller ball, and it's chosen so that the shrinking here compensates when I add ZL plus 1, okay? So this is just the intuition that, yeah, on bigger coordinates, my ball is smaller and small. Okay, and then once I have this ball that's invariant, I can use it to synthesize an invariant. Okay? Okay, let's move on to the third convenient block case. So it's where when I have a non-diagonal block. So I'm just saying that, so here I'm not looking at the last non-zero coordinates, but just, yeah, I'm looking at the last non-zero coordinate and the coordinate just before. So actually it's the coordinate just before that's gonna diverge, okay? Let's look at this. So let's just do the reasoning in this small case, but it's the same with a bigger matrix, okay? So what happens? So I have x2 that's non-zero. So if I look at the orbit, it has this form. So lambda is of modulus 1, okay? So this term is gonna remain the same in modulus. But then this term diverges because x2 is non-zero, okay? The n here makes it diverge. And this is what we're going to use to construct our invariant. So since it diverges, we would want to do something a bit like we did in the first case. Say that the first coordinate is big, okay? And that's my invariant. Problem is that it's not invariant, as usual. When you should say the obvious thing, it's not going to be an invariant at first. But then if I just add another condition, that the second coordinate is in the right direction, so that the norm will grow. So this is the intuition. Then I get an invariant. So I have a little drawing here. It's maybe a bit more obscure because now we're working in 2 coordinates at the same time. So I have to actually do 2 drawings. So this is my coordinate z1, and here is lambda z1, okay? And then if I take this direction and put it on coordinate 2, the invariant, this condition says that z2 has to be in this space, okay? So z1 is of modulus larger than m, so here, and z2 is in this space. And then this says that lambda z1 plus z2 is actually going to be in this space here, so it cannot go back in there. Okay, so that's basically it. Okay, so now we've done the 3 convenient block cases. So there remains the last harder case. So it's a bit more subtle, and that's where some nice stuff happen as well. So now I assume that all my eigenvalues have modulus 1, and that A is diagonalizable, okay? So we're just going to start with an example so that we see a bit what sorts of things happen. So I took this example because, so here we're going to have a first coordinate that makes a rotation of angle theta, and with theta not a rational multiple of 2 pi, okay? And then on the second coordinate, we're just gonna alternate +1, -1, +1, -1, okay? So I can draw this in 3D because we have 2 dimensions for the first complex coordinate and 1 for the second coordinate, okay? So this plane here corresponds to the first complex coordinate, and this corresponds to the second coordinate that's just gonna alternate. So this is x, and then ax is like I get on the second complex plane, and I just make a rotation of angle theta, and so on, okay? So unsurprisingly, we're having 2 circles. So we have an orbit that's dense in the union of these 2 circles, okay? So the invariant I would want to take is the union of these 2 circles, which is the closure of the orbit, okay? And in this case, it's semi-algebraic. So in this case, what happens? Well, if y is out of the union of these 2 circles, then this is a good invariant. And if y is inside, well, then there's no good invariant, okay? So we're going to see that this is what happens in general. We have an orbit which is dense in some semi-algebraic set, okay, which is going to be a subtorus of some big torus. That's the next slide. Yeah, and then we're going to see that this is computable. This closure of the orbit is computable, and that it actually has a polynomial size representation. Okay. Okay, so that's going to be like the theoretic slide. So what happens actually? So our matrix is like this with all the eigenvalues of modulus 1. And then we have a lattice of multiplicative relationships, okay? So it's the set of integer vectors that define the multiplicative relationships between our coordinates. So for instance, if an eigenvalue is a root of unity, we're gonna have, like in the previous example, we had A is, let's say, EI and -1. Okay, so this is a rotation of angle 1/2 pi or something. So this is yeah, this is going to be a dense a circle, and then the lattice. So here the only multiplicative relation we have is that the square of the second eigenvalue is 1, okay? So the lattice is just going to be generated by this vector, okay? There is no multiplicative relation on this one, okay? But then if we had another eigenvalues, so if I have a 3-3 matrix and here I have E of 2i, okay? Then I have this, I'm gonna have this lattice, and then I'm gonna have another multiplicative relation, is that like, so the square of this one times the inverse of this one is going to be 1, okay? So this is what my lattice says, okay? And then going back to this example, I had so the orbit was the union of 2 circles, okay? Okay, so let's just keep this on the board. So I have a lattice with a certain basis, okay? And then what I say is that the closure of the orbit is actually the set of points of complex vectors with points of modulus 1, such that they have all the same multiplicative relationships, okay? So for instance, in this example, the multiplicative relationships is just that the square of the second coordinate is 1, okay? So this gives me here, for this, it's gonna give me 2 circles, because it's just that I have, so this gives me the set, so Z in S1 squared such that Z2 squared is 1. Okay, so this is these two parallel circles, right? Okay. Okay, and then this, I can write it, once I have the basis, I can write it as an intersection of these, and these are just, this is just a polynomial in the coordinates. So this is a semi-algebraic set, okay? So there's a few things to see here. First, we should prove this equality, okay? And there's something else that we should prove is that this is all computable, right? Okay, so I have two theorems, one that will say that this is an equality, and the other one that will say that that will give a polynomial bound on the size of the vectors in the basis. Okay, so this tells me that it's computable and that it has a polynomial size representation. Okay? Yeah, so there's this, so this was the equality of the previous slide. So this is given by a theorem of Kronecker in Diophantine approximation. And then there's the other part that it's computable is a deep theorem of Masser in algebraic number theory. These were tools that were used like 3 or 4 years ago in a different paper to show stuff about linear recurrent sequences. Yeah. Okay, and then there's just that any semi-algebraic invariant must contain the closure of the orbit. This is quite obvious if you put closed semi-algebraic invariant. It's actually true for any semi-algebraic invariant. And this is just a little bit of topology. So as a conclusion, we have in this setting a semi-algebraic invariant exists if and only if the closure of the orbit is 1, because it's always semi-algebraic. It's always, and since we have this condition, we have the reverse, okay? And this is if and only if y is not in the closure of the orbit. Okay, so quick recap of the proof. Then I'm gonna go to the conclusion. So the strategy is this. If there exists a convenient block, then we can always construct an invariant using the convenient block, okay? So a convenient block is that such that I have an eigenvalue that's not 1, or if A is not diagonalizable, okay? Then I can construct an invariant. Otherwise, then A is diagonalizable and all eigenvalues have modulus 1. And then here I have, so that was the previous case where the orbit is dense in some torus and I just have to check whether Y is in the torus or not. Okay. So this was about the semi-algebraic, but what other problems can we think of that are related? So first, what happens with semilinear sets? So as we have seen, it's a bit less positive. Sometimes Y will be not in the closure of the orbit, but still there won't be any semilinear sets. But can we characterize these cases? So that's what we've done more recently. So yes, we can characterize, but actually it gets pretty ugly. So in some cases we can treat them just the way we did this. So maybe we're gonna see this. Do I have 5 minutes or? Okay. Yeah, and the big. So what's really nice with semilinear is that if I give you a semilinear set, then if I represent it as a union of convex holes, okay, then you can check just by checking on these points whether it's invariant or not. With semi-algebraic sets, you can still check it, but it's in p-space in general, so it's a bit harder. So this is really good with semilinear invariants. Yeah, and some cases of the proof, they expand to semilinear, they extend to semilinear, and but some cases of the proof they don't work anymore. Okay, another idea would be not looking at do we reach a point, but do we reach a larger set? So for instance, do we reach a ball, or do we reach a half space? So these are both hard questions that are not known right now. People are working on this in Oxford. But it seems quite hard because it's related to the Skolem problem. So the problem of does the orbit reach a given hyperplane or not, which is an open problem. We don't know if it's decidable or not. Yeah, but there are some conjectures for this case. Yeah, some people are working on this. Okay, I don't know if I should end there or show you some of the stuff on semilinear.
You can take 2 minutes.
Okay. So what still works with semilinear is that we can still do the base change. This preserve a semilinear set. So the shape of the proof can remain the same. And then we can see we can do the 4 cases again and see what happens with semilinears. So first, if there's an eigenvalue with modulus different from 1, so for instance, bigger than 1, we had this invariant. We can have a semilinear invariant in this case by just saying that we take the first few points, and then at some point, y is going to be is going to be in the convex holes, in the convex hole of my points. And then at this point, I just take, the complementary of the convex hole, and this gives me a good invariant. What happens if lambda is smaller than 1? So we had this special ball that's smaller and smaller on the coordinates. We can also have a semilinear invariant, and well, the construction is pretty ugly and complicated, but it's really the same idea that if we can control and have it as small as we want on the big dimension, then we can also have it as small as we want on the working dimension. Kind of the same idea. So this is the last case, okay, of the torus. So we had a canonical minimal semi-algebraic invariant, and it's the same for semilinear. We can construct and we have a small representation for a canonical minimal semi-linear set. So in this case, it's going to be these 2 parallel planes, okay? So we're not so happy because the minimal semilinear invariant is really big, and for instance, in the case of the circle in the plane where it's going to be the whole plane, right? But we can characterize it, so that's still something. And then there's this last case, okay, so the non-diagonalizable case. So this is where it gets really ugly with semilinear sets. So in my semi-algebraic, I had a condition here that's really quadratic, okay? Yeah, that's the dot product of my 2 coordinates, and it says that to be invariant, I have to have the second coordinate that points in the right direction, and this is basically a quadratic condition. So if lambda is a root of unity, I can still have a semilinear. I'm not going to detail it, but it's kind of there's still a way to write this in a semilinear setting if lambda is a root of unity, because we have basically a finite union. But if lambda is not a root of unity, then this fails. There's no semilinear. Yeah, so that was hard to prove, but we did it like a little while ago. So now there's no dot marks anymore. We know that if lambda is not a root of 1, there's no semilinear invariant. Okay, so this concludes my talk, and you have a nice little semi-algebraic invariant picture. Yeah. Okay, thank you.